Good day, I'm Norman Walberger. Today we're going to have a look at two very beautiful and important results due to Fermat and Euler, which help us greatly when we're working with this modular arithmetic. These are very insightful and actually fun kind of results. And to motivate this, let's just first set the scene again. So we are talking about modular arithmetic, and I remind you that n mod m equals r. That means that r is the remainder when n is divided by m. And we said that k is congruent to L mod m precisely when k mod m equals L mod m. In other words, when k and L have the same remainders mod m. And then we had this theorem that I stated, which was that if two numbers k1 and L1 are congruent mod m, in other words, have this property, and k2 and L2 are also congruent mod m, then the product of k1 and k2 is congruent to the product of L1 and L2. So arithmetic mod m works very much like ordinary arithmetic. So as an application of this pleasant result, suppose that we know that 8 to the 10 is congruent to 12 mod 13. That's actually a true fact. All right. And suppose we were interested in finding out what 8 to the 11 was congruent to mod 13. It's really asking what the remainder is when you divide 8 to the 11 by 13. So one thing we could do is we could take 8 to the 10, well, we could compute 8 to the 11 essentially and divide by 13. But the point is that if we already know what this thing is congruent to, then all we really have to do is use this theorem and multiply both sides by 8. Right? 8 is congruent to 8. So if we multiply both sides by 8, then we get 8 to the 11 is congruent to 8 times 12. Now 8 times 12 is 96, and that's 5 more than 91, which is a multiple of 13. So 8 times 12 is congruent to 5 mod 13. And this allows us to calculate the remainder of some biggish power of a number without actually having to go through the trouble of actually computing the number itself. So let's have a look at these powers of 8, for example, mod 13. Okay, so 8 to the 0 is 1, 8 to the 1 is 8, 8 squared is 64, but modulo 13, 64 is the same as 12, because we can subtract 4 times 13 is 52. Now I just note that 12 is really the same as minus 1. These two numbers differ by 13, so sometimes it's more convenient to think of 12 as being minus 1. Okay, now to get 8 cubed, we would multiply the previous one by 8. Now we could multiply the 12 by 8, or in fact the 64, but it's nicest to multiply the minus 1 by 8 to get minus 8, and that's congruent to 5. Just add 13. Then 8 to the 4, we multiply the previous one by 8, that gives us 40. And 40 is congruent to 1 because we can subtract 39. So in this game, any multiple of 13 counts as essentially 0. We can add or subtract it without affecting anything. Multiplying by 8, we get 8 to the 5th is congruent to 8. And then the pattern continues because we're at the same stage as we were there. Then 8 to the 6 is congruent to minus 1, 8 to the 7 is congruent to 5, 8 to the 8 is congruent to 1, and it repeats again, 8 to the 9 is 8, and then minus 1, and then 5, and then 1. So we see that we have repetition here going on with period 4. And we can summarize that in this little formula here that says that 8 to the n plus 4 is congruent to 8 to the n. So when you add 4 to the exponent, you haven't changed the residue or the modulus or the remainder mod 13. And on the right hand side here I've just listed some of the multiples of 13, which is sort of convenient if you're doing this kind of modular arithmetic, say mod 13. So this is a very important fact that if we look at a fixed modulus and a fixed number, just powers of that number, that we end up in some kind of cyclic loop. There's a periodicity happening there, and that's sort of the key to this modular arithmetic story here. So that was interesting. But since we're mathematicians We want to understand what's going on. We want to zoom out a little bit and see what the bigger picture is. So to try to get a sense of that, here is a table of powers of not just 8. Here are the powers of 8 that we basically just had a look at in the previous slide, but powers of all the other numbers modulo 13 as well. So we're doing arithmetic here, mod 13. This is a table of n to the k, where n is one of the numbers from 1 to 12, and k is a power, well, starting with essentially 1, and then 2, 3, all the way up to, say, 12. Okay, it's very instructive now to make such a table, and we can do it relatively simply because we don't actually have to take these big powers. We just have to multiply every previous one by whatever we're considering. So for example, at any one of these rows, if we want to say look at the powers of 4, 4 squared is 16, which is congruent to 3. And then to get the next power, we multiply this previous one by 4, giving us 12. Multiply this one by 4, it gives us 48, which is 39 plus 9, so it's congruent to 9, and so on. So what do we see? Well, there's some very nice patterns here, but it's also not entirely obvious what the overall story is. Let's observe that very important issue is that when we get to the 12 column, that all of the numbers are 1. That's the most important fact about this story. There is 1 scattered elsewhere, and depending on the number or the row that you choose, the 1s are appearing at some regular intervals. So here they're appearing every 3 times. There's a periodicity of 3. While over here, say, the periodicity is every 6. And over here it's periodicity 4. And over here, well, there's no periodicity. It goes all the way up to 12, and then it repeats. So if you haven't seen this kind of thing before, it's well worth having a very close look at this. It's natural to look at something like this and say, this is great. This is a source of fun and investigation. And I can do the same kind of thing looking at, say, powers not mod 13, but mod some other number. And then compare, do the same kinds of things happen. So what you'd really like to be able to do if you really understood this is be able to substitute any number for the 13 and sort of beforehand be able to predict largely what's going to happen with this table. Right? That means that you really understand what's going on. But drawing up the table, doing that legwork first, is a kind of necessary preliminary to understanding the pattern. Now originally I gave you the exercise of trying to figure out what happens with z when you divide it by 13. And z has lots of powers of 10, so it makes sense for us to look at what happens with powers of 10 mod 13. And if you look at the previous table, you see that the powers of 10 repeat every 6. So 10 to the 6 is congruent to 1, and then afterwards it repeats. And the various powers are 10 squared is 9, and then 12, and then 3, and then 4, and then when we get to 6, we get to 1. And after that it repeats, namely 10, 9, 12, 3, 4, 1. 10, 9, 12, 3, 4, 1, and so on. So that means that if we want to understand 10 to the n mod 13, we really need to understand n mod 6. There's now a 6-fold symmetry that's appearing here in the fact that these remainders repeat every 6. So if we have a very big power there, we really want to know where does it sit in this pattern of multiples of 6 that will determine which of these various remainders we actually end up on. So let me illustrate that with this example. Suppose we have 10 to the 398 mod 13. We want to figure out what that is. In other words, we want to figure out what the remainder is when we divide 10 to the 398 by 13. Okay, so let's note that 398 is 66 times 6 plus 2. In other words, if I divide it by 6, I get a quotient of 66 and a remainder of 2. All right, so in modular arithmetic language, that's saying that 398 is congruent to 2 mod 6. The remainder that you get when you divide it by 6 is 2. We're talking about this exponent up here. Knowing that, we can now do the following computation, mod 13. Okay. We now can say that 10 to the 398 is equal to 10 to the 6 times 66 plus 2. And now I'm going to rewrite this just using ordinary rules for exponents. This 10 to the 6 times 66, I'll write it as 10 to the 6 to the 66. And this plus 2 gets represented by multiplying by 10 squared. All right, so just usual laws of exponents for ordinary numbers tells us those two are equal. But now since we're working mod 13, okay, the 10 to the 6 we've seen is congruent to 1. So we're allowed to replace this thing inside the brackets with a single 1. That's great, because then this thing to the 66 power will be congruent to 1 to the 66. And that is very simple to calculate. 1 to the 66 is just 1. 10 squared is congruent to 9. So this whole thing becomes just 1 to the 66 times 9, or 9. So this number, mod 13, is 9. It gives a remainder of 9 when you divide it by 13. And we've analyzed that by looking at the exponent and basically analyzed it modulo 6. So it's very interesting that this original problem that has to do with divisibility mod 7 ends up converting, at least partially, to a question about divisibility of the exponent mod 6. Okay, that's great, but we still have quite a ways to go if we want to get to z. How do we deal with a tower of exponents? Well, let's look at a simpler example. Let's look at 10 to the 10 to the 10 mod 13. See if we can get our heads around that. So we know that working mod 6, powers of 10 follow this pattern. So 10 to the 1 is congruent to 4 mod 6. 10 squared is congruent to, well, if we multiply this by 10, we get 40. And now mod 6, 40 is the same as 4, because we can cast away 36, which is 6 times 6. So 10 to the 1 is congruent to 4, and 10 squared is also congruent to 4, mod 6. But then 10 cubed will also be congruent to 40, which is 4, mod 6. So then the pattern will just keep on repeating, that all these powers of 10, 10 to the n, will all be congruent to 4 mod 6 if the power is at least 1. Won't be true for n equals 0, but if we start with 1, then it will be true for any power that we get to from there. So 10 to the 10 is congruent to 4 mod 6. And so now if we switch to mod 13, here now is the mod 13 calculation. The original 10 to the 10 to the 10. We've just decided that this 10 to the 10 here is congruent to 4 mod 6, so that this whole thing here, this 10 to the 10, can be replaced with 6L plus 4. That's what this is saying, that it's a multiple of 6 plus 4. And I don't really care what that L is, as we'll see very shortly. It's just some multiple of 6 plus 4. It's the plus 4 that's critical. And why that is because when we write this now using our exponential laws or rules, this 10 to the 6L becomes 10 to the 6 to the L, and the plus 4 means we multiply by 10 to the 4. And then we get the same trick that happened last time. The whole point was that we knew that 10 to the 6 was congruent to 1. That was the big simplification. 10 to the 6 is congruent to 1, and so that means we can replace this thing with a 1. That means that whole thing here simplifies just to 1 to the L, which is just 1. 10 to the 4th is congruent to 3 mod 13, and so we end up getting just the whole thing is congruent to 3 mod 13. We can appreciate that we haven't gotten anywhere near actually dividing this huge number by 13. That might be a major pain to do, okay? But in order to get at its remainder, we can use this indirect reasoning having to do with this observation that the remainders are cyclical. In fact, they're cyclical with the period 6. So once we get our head around to sort of how many periods of 6 there are and what the remainder is mod 6, then we can unravel the remainder with this very pleasant kind of arithmetic in the modular world. Alright, so now let's finally address this challenge that I've given you to figure out what is the remainder when you divide z by 13. So in other words, we want to calculate what happens to z mod 13. And let's note that this 10 triangle 10 here, which is this tower of 10 tens as exponents, is really 10 to the exponent 10 triangle 9. So it's 10 to the exponent. What's sitting on top of the 10 as an exponent is 10 triangle 9. Okay, now we've seen that to figure out what some power of 10 is congruent to mod 13, we should look at the exponent and try to figure out what its remainder is mod 6. So let's do that. Let's take this exponent, 10 triangle 9, and look at it mod 6. Well, actually, that's, in this case, very easy. 10 triangle 9 is congruent to 4 mod 6. Why is that? Well, that's because it's a power of 10. We've seen that all the powers of 10, 10 to the 1, 10 squared, 10 cubed, 10 to the 4th, all of them are congruent to 4 mod 6. Because the first one is congruent to 4 mod 6, and then the next one will be 10 times that, which is 40, which is also congruent to 4 mod 6. So 10 triangle 9 will also be congruent to 4 mod 6 just because the pattern is completely uniform. Now, that means that we can think about z, which is 10 to the 10 triangle 9 plus 23, as 10 to the 6k plus 4. This number, 10 triangle 9, is congruent to 4 mod 6. That means it can be expressed as 6 times some number k plus 4. And we don't know what that k is. It's going to be some humongous number, but we don't need to concern ourselves with it. It's the plus 4 that's important. Alright, now we do the same thing that we did with the other examples. We look at this 10 to the 6k plus 4, and we rewrite it as 10 to the 6 to the k times 10 to the 4. We still have a plus 23 out here. And pleasantly, 10 to the 6 we've seen is congruent to 1 mod 13. So this big term here, this whole thing here becomes just 1 to the k, a huge simplification. 10 to the 4 is congruent to 3, so we end up getting 1 times 3 plus 23 mod 13, and that's 3 plus 23, which is 26. And 26 happens to be 2 times 13, so that's actually congruent to 0 mod 13. It means that the remainder, when you divide z by 13, is 0. So z is actually divisible, not just by the prime 3, but also by the prime 13. So we found out that even though this number is so huge, there's no way we could write it out in Hindu-Arabic form. There's big problems in actually trying to explicitly divide it by 13. Nevertheless, we can use this indirect argument, this computation which is really done in the language just of modulo 13. We can deduce that this big Z is actually divisible by 13. So very interesting. And this all goes back to my series, Famous Math Problems. So Famous Math Problems series, this is actually the first video in that series, deals exactly with the factorization of this Z. And quite a few people had some investigations on that. And in particular, one viewer, Relike868, made a very nice calculation, and in fact went through the other primes, less than 100, and figured out that, just by computing, that in fact these are the only two primes that are less than 100 which divide Z. If you'd like to see that computation, he's actually written it up, so if you go to Famous Math Problems 1, you can find the link, but also I will put a link in the description of this video. Alright, so good stuff. So we can, at least in principle, get at these humongous congruences using this kind of trickery and this real understanding of what happens to powers. But we want to understand that a little bit more carefully. So what actually is the rule that we're using, the general rule that we can extract from this kind of thinking? That goes back to the great French mathematician of the 17th century, Pierre Fermat. So before we get to Fermat's lovely theorem, let me point out that there's lots of applications of modular arithmetic that are actually quite connected to daily life. They're not all so exotic as trying to figure out what the remainder of Z is when you divide it by 13. So for example, there's questions like the following. If today is Tuesday, what day will it be, say, in a certain number of days? Say in 1,000 days. 1,000 days from now, what day of the week is it? Well, this is sort of obviously a congruence kind of problem because days of the week correspond to modulo 7 arithmetic, because the days of the week repeat every 7. So what we're really interested in is calculating what 1,000 is mod 7. Alright, so let's make that calculation. So what's the remainder that you get when you divide 1,000 by 7? So let's do it in a little bit of a different way than previously. So instead of actually dividing 1,000 by 7, let's think about throwing away multiples of 7. So an obvious multiple to throw away is 700. 700 is the same as 0 when we're working mod 7. So if we throw away 700, it really hasn't changed anything, but then the 1,000 becomes 300. That's simpler. So we employ the same strategy, look for a nice multiple of 7 that we can toss away. We can write 300 as, say, a 280 plus 20, recognizing that 280 is going to be a multiple of 7. And so the 280 disappears and we just get congruent to 20. And then we just throw away 14 and we get 6. So we see that 1,000 is congruent to 6 mod 7. So 1,000 days from Tuesday is, as far as days of the week concerned, the same as 6 days from Tuesday. And 6 days from Tuesday is Monday. So if today is Tuesday, then in 1,000 days it will be Monday. Okay, so there's a very pleasant, famous kind of problem of trying to figure out, what day of the week it is at some given day in history or maybe in the future. January 19th, 1304. What day of the week was that? Well, that rests exactly on this modular kind of arithmetic. So, for example, relevant to that question is, what day will it be in one non-leap year? So, 1 year has 365 days. So if we go exactly 1 year from today, how many weeks have gone by? Well, it's a question of dividing 365 by 7 and seeing what the remainder is, or another way of thinking about it, just throwing out multiples of 7. So 350 plus 15, that's another way of writing this. The 350 is a multiple of 7, so we can toss it aside, and we see that 365 is congruent to 15, which is congruent to 1 mod 7. And that's telling us that in 1 year, the day of the week advances by exactly 1. So if today is January 1st, then next year on January 1st, it will be 1 more day in the week than it is today. So if today is, say, Tuesday, then the next January 1st will be Wednesday, and then the next January 1st will be Thursday, and so on. But of course we have to remember leap years, right? In a leap year there is one extra day, so if we're talking about a leap year, then we have to incorporate that, and then the day shifts not just by 1, but by 2. So you can kind of see that this kind of question of figuring out what day it was, back at some historical time, or in the year 2079, July 15th, what day of the week is that going to be? Well, a little bit of modular arithmetic, taking into consideration that every year advances you 1 and every leap year advances you 2, then it's not so hard to work such questions out. So here is Pierre Fermat's lovely observation or theorem. It's a direct generalization of the fact that we saw that mod 13, the 12th power of all the numbers, at least all the non-zero numbers, were all congruent to 1 mod 13. It's a very direct generalization of that observation. So the statement is that if p is a prime, that's the crucial thing, p is a prime number, and p does not divide n. So we have some other number n which is not divisible by p. Then n to the p minus 1 is congruent to 1 mod p. If you take that n to the p minus first power, for example, if p is 13, then we're talking about the 12th power, then when you raise it to the 12th power, you're going to get 1 mod 13. So in general, n to the p minus 1 is congruent to 1 mod p. So this is the one that we've already seen, that mod 13, n to the 12th will be congruent to 1 mod 13. As long as n is not actually divisible by 13, or congruent to 0. And say mod 5, a simpler modulus, if n is not congruent to 0 mod 5, then n to the 4th will be congruent to 1 mod 5. And we can say a simple table of powers here. This is a table of n to the k mod 5, powers of 1, powers of 2, powers of 3, powers of 4. For example, 3 times 3 is 9, which is the same as 4. Then multiply by 3 again. 3 times 4 is 12, which is the same as 2 mod 5. And 2 times 3 is 6, which is the same as 1 mod 5. So in each of these non-zero cases, so 1, 2, 3, or 4, once you raise the number to the 4th power, you get 1s. Now, if this was a course in number theory, I would want to, and it would be obliged to, give you a proof of Fermat's theorem. But that's probably best done after we've done some group theory. A little bit of group theory makes that a lot easier to understand. And we probably will do a bit of group theory at some point, and then we may have occasion to talk a little bit about Fermat's theorem and its proof. But I want to ask a very natural sort of extension question. What happens if we consider the same story but the modulus is not a prime number? Fermat's theorem tells us what happens if our modulus is a prime number p. But what happens more generally? Well, the great Swiss mathematician Leonhard Euler figured that out. And the statement's a little bit more complicated than Fermat's theorem. It involves an auxiliary function called Euler's phi function, sometimes also called a totient function. So let's talk about the phi function of Euler. Okay, so m is a natural number. Phi of m is what? Well, it's the number of numbers less than m which are relatively prime to m. So it's the size of a set, the set of k, where k is a natural number here, everything is a natural number unless I say otherwise, set of k such that k is between 1 and m, including 1 possibly, but less than m. And such that k and m are relatively prime. And that means that they have no common factor. No common factor at all between k and m. So we look at that set, the set of all such numbers less than m which are relatively prime to it, and we take the size of that set. how many such numbers there are, and that's 5m. So for example, 5, 2. There's only one number which is less than 2, which is relatively prime to it, namely 1. 5, 3 is the size of the set 1, 2. So it's 2. 5, 4, the size of the set 1, 3. These are the numbers less than 4, which are relatively prime to it. The numbers less than 5, well, those are all the numbers, because 5 is a prime. That's why we get 4. 5, 6, well, there's only 1 and 5. The other numbers have common factors. So 5, 6 drops down to 2. 5, 7, well, 7 is a prime, so every number is relatively prime, and that's 6. 5, 8, you can check is 4. 5, 9 is the number in this set. Here are the relatively prime things. That's 6. 5, 10 is 4. 5, 11 is 10 because that's a prime. And 5, 12 is 4. And it goes on. There's a kind of a pattern, but the pattern depends very much on how far away this number is from being prime. So you really want to know the prime factorization of this number before you can easily write down, for bigger numbers, the Euler phi function for it. Okay, so here is Euler's generalization of Fermat's theorem. It tells us what exponent we need to raise a number n to in order to get a remainder of 1 modulo some other number m. And in this case, m does not have to be prime. If m is prime, then this formula reduces to Fermat's theorem. So it's a generalization of Fermat's theorem. So the statement is that if n and m are relatively prime, and I remind you that means they have no common factors, like 7 and 6, or 6 and 11, but not like 10 and 8. They have a common factor. So if n and m are relatively prime, then n to the phi of m is congruent to 1 mod m. And the interesting thing is that the exponent here works for each of these numbers n, which are relatively prime to m. The exponent only depends on m. So if you know m, you can calculate phi of m, then you know the magic number that you need to raise any other relatively prime number to in order to get that beautiful 1 that makes so much of this modular arithmetic much simpler. So let me illustrate this at least quickly by showing you these tables of powers where our modulus is not a prime number anymore. So here's the case when the modulus is 6. M is 6. And the phi of m happens to be 2. So here are the numbers from 0 up to 5. And here are the various powers mod 6. So there's 2. 2 squared is 4. 2 cubed is 8. But 8 is the same as 2. Then we multiply that by 2, get 2 to the 4th, that's 4. 2 to the 5th is 2. Notice that there's no 1 appearing here. There's no way of getting a remainder of 1 when you take powers of 2 mod 6. In fact, Fermat's theorem doesn't apply, Euler's theorem doesn't apply to this because 2 and 6 are not relatively prime. But say 5 and 6 are relatively prime, and if we look at powers of 5, well, it's not too hard. A 5 squared is 25, which is the same as 1. So it goes 5, 1, 5, 1, 5, 1, etc. But Euler is saying that if we look at just the second power, 5m equals 2, then whenever we have a relatively prime number, namely 1 and 5, then their square will be congruent to 1 mod 6. That's maybe even a little bit too small to see what's going on. So here's a little bit of a bigger table where m is 8. We're working mod 8. Here are the various numbers, remainders mod 8, and here are various powers mod 8. So there's 3 to the 1, 3 squared, 3 cubed, 3 to the 4th, etc., all the way to 3 to the 7. And phi of m is 4. So Euler tells us that we should expect to see 1s in these 4th powers. fact, we do see 1s, but we also see 0s. We see 1s exactly here at the 1, the 3, the 5, and the 7. These are the numbers which are relatively prime to 8. 1, 3, 5, and 7. Note, perhaps curiously, that, say, powers of 2 do a somewhat curious thing. So 2 squared is 4, and then we multiply that by 2, we get 8. But 8 is congruent to 0. And then after the words, we still just get zeros forever after that. So Fermat's theorem, Euler's theorem, gives us a lot of information about powers of numbers in this modular arithmetic setting. And they are pillars of modern number theory, and they're also very important in modern internet security, with various encryption, decryption algorithms that rely essentially on them. And those kind of algorithms also take into consideration the relative difficulty of being able to find phi of m when m is a very big number. It turns out that that's intimately connected with the thorny problem of factoring m into primes, which was all of what famous math problems number 1 was all about. So this question of, given a big number m, a natural number, how do you factor it into primes? Can you always factor numbers into primes? Well, that is a subtle question. So we're going to have to say some non-standard things about unique factorization, okay? So that's what we're going to do in our next video. We're going to have a look at unique factorization for numbers. Does it really work? I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.